Okay, this lesson is about acids and bases. I think a few things that I'm going to say are going to be review and familiar from previous courses, um, but maybe there'll be a few new things here too. So, first, we're looking at properties of acids and bases. Maybe, you can think of a common food product or something that comes to mind that would be a typical acid. So maybe you thought of vinegar or lemon juice, perhaps Coca-Cola with the phosphoric acid. Maybe you thought of battery acid. I know that's not a food. Sulfuric acid and battery acid, or stomach acid, hydrochloric acid. Maybe you thought of sour keys. The citric acid that's sprinkled on sour keys gives it its sour flavor. So certainly the tastes of acids, you can think of a lemon or vinegar or sour keys, they taste sour. Bases, on the other hand, pure cocoa, really in a lot of our cleaning products, which you're obviously not going to taste, but bases tend to taste bitter. How do acids feel? Well, if you have a paper cut, certainly if you squeeze some lemon juice or spill some vinegar on your finger with a paper cut, it's definitely going to sting. And that's something to note, that both acids and bases are corrosive. But in terms of the feel, really, if you didn't have that paper cut and you spilt the vinegar on your fingers, it doesn't really have a characteristic feel. If anything, we could describe it to be like water. So that's not a characteristic feel, but we could say it's like water, feels like water. Whereas a base, if you spilt a cleaning agent, maybe you're cleaning the bathroom and you got some of the cleaner on your hands if you weren't wearing gloves, which would be a good idea because those substances are quite corrosive, but they definitely feel slippery. You could even think of soap as feeling slippery also. Now, what about reaction with, I have reaction with acid here. That should be reaction with metals. So how do metals react with acids? Well, if you think back to single displacement reactions, magnesium and acid, for example, you'll recall that they do react, right, and produce hydrogen gas. Bases, on the other hand, that's an H2, by the way. Bases, on the other hand, there'll be no reaction with the metals. What about metals with carbonate compounds? Acids with carbonate compounds. So vinegar, the acid, baking soda, sodium bicarbonate, the carbonate or bicarbonate compound, and definitely you can think of the fizzing that's produced as those two react. So we find that carbon dioxide gas is produced. Bases, no reaction with carbonates. Carbonates, in fact, are bases themselves. So electrical conductivity, well, I'll put a little star beside this because we'll revisit this with acid-base strength, but typically acids and bases are good conductors. So we'll look at how they can possibly be poor conductors a bit later when we look at acid-base strength. Okay, pH, perhaps you're remembering this. We'll talk a little bit further about pH below, but anything less than 7 is classified as acidic and greater than 7 as basic. We'll see 7 to be neutral. We'll have a look at litmus paper in class if you haven't seen it before, but it comes in two colors, red litmus paper and blue litmus paper. And if you test them both in a neutral solution, they each remain the same color. But once you drop acid, the blue one will change to pink. The pink one or the red one stays red, but the blue one becomes red. And so the idea is that both litmus papers will be red in acid. So the red one stays red, the blue one turns red. In base, the red one will turn blue and the blue one stays blue. If they both stay their original color, red stays red and blue stays blue, then that's neutral. Phenolphthalein is an indicator, and again, we'll have a look at these in class, but it's colorless in acid and a bright pink-purple, almost a fuchsia color in base. Bromo blue is typically yellow in acids and blue in base. So you're going to see, I'll bring in some other indicators too. There's a whole range of colors. The acid-base indicator chemistry is really quite pretty and kind of fun to play with. So we'll definitely look at that in class. Okay, so Arrhenius theory. There's a few different theories of acids and bases. The one we look at in this course is the very basic Arrhenius theory. And so the idea here is that acids, an Arrhenius acid, so an acid that's recognized as an acid by Arrhenius theory, is recognized as such because it ionizes in water to form the hydrogen ion. So what do I mean by ionize? Well, here's an HCl molecule. If these electrons in that covalent bond stay with that chlorine atom, then we have the original 7 valence electrons of the chlorine atom plus the hydrogen electron, and so now we've formed a chloride ion. That hydrogen nucleus is now all on its own, just a proton. Without its electron, the particle has a positive charge. And so we use the term ionize here because this substance was a molecule, H covalently bonded to Cl, and now ions have been formed. And so we represent those as H positive AQ, surrounded by water molecules, and the chloride ion. And so the Arrhenius theory recognizes a substance as acidic if on the right side, on the product side, you see the hydrogen ion formed. Now, if you dissociate the ionic compound, sodium hydroxide, it will break up into sodium ions, again in water, it's surrounded by water molecules, and hydroxide ions. And Arrhenius theory recognizes a substance as a base, so sodium hydroxide as an Arrhenius base, if it produces hydroxide ions in solution. Now, this theory itself is a little bit limiting because, first of all, it requires water to be the solvent, and that's not always the case, although it is very common. And secondly, there are substances that actually have pH greater than 7, and yet Arrhenius theory doesn't recognize them as basic. So in later courses, we will investigate other theories of acid-base chemistry, but for now, this Arrhenius theory is going to be useful for us. So I'm asking you to prepare for a class activity by completing the prediction column, so the middle column in this table. So this part here we're going to do in class. I'm going to have some pH paper or an indicator for you to be able to measure the pH of these actual solutions. But what I'd like you to do is write equations the way that I did for HCl and NaOH and predict based on the Arrhenius theory lesson here whether you think these substances are going to be acidic or basic. Okay, so run the list, write equations here, and make your prediction of acid or base. So you're writing an equation the way we did for sodium hydroxide or the way we did for HCl. So try to do that and see what you come up with, and leave this column blank. We're going to test them in class and you'll see what you come up with. Okay, moving on. Looking at pH. pH actually stands for power of hydrogen, which really means that we're communicating the hydrogen ion concentration. Now, the hydrogen ion concentration in solutions, everyday solutions, are typically pretty small values, like 0.1 moles per liter. Or, in water, it's 1.0 times 10 to the negative 7 moles per liter. In vinegar, it might be 1.0 times 10 to the negative 3 moles per liter. So we've got some pretty small numbers. And not only that, scientific notation comes into play. And all of these values are, maybe a little bit more laborious to actually talk about. It's much easier to say, oh, lemon juice has a pH of 2. Milk has a pH of 7. Bleach has a pH of 12. And so these pH values are actually based on a logarithmic scale with a base of 10. So the idea here is that the base is 10 and the exponent is the negative of the pH value. And this is the hydrogen ion concentration in the solution. So if you look at the hydrogen ion concentration in this first example here, you'll see I have 0.1, right? You can plug this into your calculator, negative log 0.1 equals, and see what you get. Or your calculator might work where you plug in the 0.1, then the log, then multiply by -1. But either way, you should be getting 1. And just to show you why that works, 0.1 is really 10 to the -1. So remember, the pH is the negative log. It's the negative of the exponent. So here's your exponent here. What's the negative of -1? +1. So that's why when you plug it into your calculator, you're getting an answer of 1. So when the pH is 1, we're way down here, right, in the very acidic range. So that could be for a hydrochloric acid solution. As you can see, I've labeled in green, pH values that are pretty low here are very acidic. When the pH is a little bit higher, but not yet 7, right, this is the range of being slightly acidic. pH of 7 is neutral. When you get on the other side of neutral, we start to be slightly basic, moving up towards very basic. You know, is it possible to have a pH value even negative, less than 0? It is, but in that case, the concentration of the hydrogen ion is much greater than what we would commonly see in solutions, and therefore, you know, you typically, in practice, are not going to see those negative pH values. So here's an example of the hydrogen ion concentration in neutral water, 1.0 times 10 to the -7. So if you plug that into our pH formula, you'll find that you get a pH of 7. And again, focusing on the exponent on the power of 10, here the exponent is -7. So if the pH is the negative of the exponent here in the concentration, the negative of -7 is +7. So again, the pH is just set up to be a really convenient way of communicating the hydrogen ion concentration. So a pH of 7 is neutral. That's where, due to water ionizing itself to a very small degree, we have the hydrogen ion equal to the hydroxide ion concentration. So hydrogen ion is associated with acidic solutions, hydroxide is associated with basic solutions, and when the concentrations of these two are equal, the solution is neutral. In the acidic side, if the hydrogen ion concentration is greater than the hydroxide, we'll have pH values less than 7. When the hydroxide ion concentration is greater than the hydrogen ion, then we'll see pH values greater than 7. Okay, so one last calculation here. I'm just looking to set up a trend here. Given this hydrogen ion concentration, we plug it in to our calculator or figure it out using your understanding of logs, and we come up with 13.00. Now I'll just make a comment about this calculation and why I only put 1 digit after the decimal here, and here I did 2 digits after the decimal. When you're stating pH values, significant figures are stated after the decimal. This concentration value here has 1 sig fig. This concentration value here has 2 sig figs. This concentration value here has 2 sig figs. We're counting the concentration sig figs the way we normally do. And so, but when we state the pH, the number in the ones position is really just placeholding a power of 10 for us, and so the significant figures come after the decimal. And that's why you see 2 digits in the pH value after the decimal, because there were 2 sig figs in the concentration in this last example. I gave you some common household examples here, but certainly you could look up some more for your interest. But, you know, lemon juice down here to pH of 2, tomatoes will be somewhere in here, milk is pH of 6. Your blood pH is carefully controlled. It's hazardous to be outside of the normal range, but really 7.35 to 7.45 is kind of the optimal range for the pH of your blood. Antacids can be pH of 9 or 10, bleach upwards of 12, sodium hydroxide solutions up here 13, 14. So you'll notice that lots of cleaners are on the basic side and lots of foods are on the acidic side. Okay, one last point here about pH, and I'll try to keep my pH scale on the screen so we can refer to it easily. Looking to complete the blanks in these two statements at the bottom. So pH of 2, here we are here, is how many times more either acidic or basic than a pH of 5. So I'll just mark the pH of 5 here. And you might think, well, from 2 to 5, that's 3 times. Well, because these pH values are powers of 10, that pH of 2 is actually 10 to the 3. The pH values are the exponents. So it's actually 10 to the 3, or 1,000 times more acidic than a pH of 5. So a pH of 2 to 5 is actually quite a difference, 10 to the 3 or 1,000 times more acidic. So can you complete the second statement? A pH of 10 compared to a pH of 8. So pH of 10 is how many times more, either acidic or basic, than a pH of 8? Okay, hopefully you were thinking 10 to the 2, which is 100 times more basic, seeing as the 10 is greater than the 8. All right, so moving on, final concept here, acid-base strength versus concentration. So I think the term strength is commonly misused or misunderstood with acid-base chemistry. So let's first start with something you're more familiar with, the idea of concentration. So over here with concentration, I'm giving you the tip, think the number of moles per liter. Remember you've been doing calculations with concentration, 2.0 moles per liter, 0.15 moles per liter. And if we put some dots in here, right, perhaps a concentrated solution might have this many dots, whereas a dilute one, right, much fewer. And so we see, and we can see that in the picture, and we can quantify it thinking of the number of moles per liter. So concentration is really about the number of moles of the solute, the number of particles of the solute in that volume of solution. Strength, on the other hand, is an entirely different concept. Strength of acids and bases has to do with the percent that they ionize or dissociate, the percent that they break up into or form ions. So when you have a strong acid or base, there's 100% of this ionization or 100% dissociation. So for example, HCl, which we know of to be these molecules, right? As I showed you before, those electrons can stay with the chlorine atom, and we form the hydrogen ion, right? And the chloride ion. Oops. So 8 electrons around the chloride, and we have the hydrogen ion. So we're either forming hydrogen ions here or chloride ions as that molecule ionizes. The idea behind hydrochloric acid being a strong acid is that 100% of these molecules ionize to form ions in solution, which means the actual types of particles that are in this solution are all ions. So I'm going to put positive and negative symbols to represent the hydrogen and chloride ions. Now, how many of these particles I draw would totally depend on the concentration, which isn't being communicated here. I'm just showing an example of a strong acid by showing positives and negatives to represent these positive and negative ions. The point is, the types of particles here are all ions. And that's the idea of a strong acid. Of course, that's going to lead to good electrical conductivity because the ions are responsible for carrying the current. Now, what about the case of hydrofluoric acid? So having a look a little bit down below here at hydrofluoric acid. Well, hydrofluoric acid happens to be a weak acid. So the same potential for the ionization exists here, where those electrons will go with the fluorine atom to form the fluoride ion. But this only happens 1 to 5% typically for weak acids. So HCl was our example here of a strong acid, right? HF is our example of a weak acid. In fact, it's not even correct really for me to put just a forward arrow there. I'm actually going to put a reverse arrow to suggest that we have many more of these molecules than we do of these ions. So there's actually very few ions in solution. I'm just going to put one of each, and perhaps I'll use a rectangle to represent those HF molecules. And so there are many more molecules of HF than there are ions. And the idea then of there being very few ions in solution and mostly molecules is the idea of a weak acid, or base for that matter. And you might expect then with fewer ions that this leads to poor electrical conductivity. So where concentration is about the number of particles of solute in the solution, strength is about the type of particle. In the case of strong acids or bases, we're going to have all ions for the solute. In the case of weak acids and bases, we're going to have mostly molecules, very few ions. So all that's left really is to communicate the specific strong and weak acids and bases. So strong acids, there are 6. Everything else is weak. So 3 oxyacids, sulfuric acid, perchloric acid, and nitric acid. Of course, each of these are aqueous, so you can jot your aqueous subscript here. And then 3 binary acids. So HCl, that go-to school acid that you see in labs all the time, hydrochloric acid. And then keep following down the halogens, hydrobromic acid and hydroiodic acid. Those are the 6 strong acids. Everything else is weak. If you've never heard of it, it's weak. Fumaric acid, acetic acid, hydrocyanic acid, chloric acid, chlorous acid, phosphoric acid, sulfurous acid, hydrosulfurous acid. Basically, these 6 are strong. Everything else is weak. Citric acid, ascorbic acid, lactic acid. You can think of a whole bunch of different acids. They're all weak. These are the only 6 that ionize completely. In terms of strong bases, it's the group 1 and 2. So think of group 1 and 2 metals, oxides and hydroxides. For example, here's a group 2 oxide, calcium oxide. Here's a group 1 hydroxide, sodium hydroxide. So group 1 and 2 oxides and hydroxides are strong bases. Everything else is weak. So some examples, aluminum hydroxide, there's group 13 metals, so that's definitely going to be a weak base. Ammonia, sodium carbonate. So the carbonate compounds, a whole bunch of nitrogen-based bases are all weak bases. Any metal hydroxide, if the metal's not a group 1 or 2, that makes it a weak base. Okay, and so it's the strong bases that will ionize or dissociate completely, and it's the weak bases, right, that will have mostly molecules in solution. Okay, I haven't reviewed acid nomenclature. That's something we've already covered in an earlier video. So if you don't recall how to name these acids, sulfuric, perchloric, nitric, hydrochloric, hydrobromic, hydroiodic, I suggest you revisit the binary acid nomenclature video, binary and oxy acids, revisit that nomenclature video.